Welcome. In chapter 13, we will look at how we can use first and second derivative to study the behavior of function. This is usually phrased in terms of graphs, but this is not really about graphing. Very often, laws, both in natural and social sciences, are expressed in terms of rates. So we want to look at how our knowledge of rate of a function, that's the derivative of the function, can be used to say something about the function itself, the quantity actually interested in. Another application is to finding maximum or minimum, the biggest or the smallest value of a function. Again, a lot of applications one might be interested in this sort of thing. For now, we are just going to make a string of definitions that very often we have a function and an interval of interest. In applications, this interval might be where the quantity actually makes sense, even if the expression we get has a bigger domain. Let f be a function defined over an interval. C is called the absolute or global maximum of f if f of c is the biggest value of the function in that interval. That is to say, for any x in that interval, f of c is at least as large as f of x. The reverse is called the absolute or global minimum. C is the absolute or global minimum if f of c is the smallest value, that is to say f of c is less than or equal to f of x for any x in that interval. Differential calculus actually only tells us about local behavior of functions. Most directly, it can only tell us about what are called relative or local extrema. So if f is a function that's defined in some open interval containing c, then we say that c is a local or relative maximum if there is some open interval containing c such that f of c is greater than or equal to f of x for all x in that small open interval. The open interval has to have a positive length but could be extremely small, extremely narrow. A relative minimum is a number c so that f of c is less than or equal to f of x for all x in some small open interval containing c. The connection between derivative and relative extrema, that's a relative maximum or relative minimum, is that if f prime of c is non-zero, c cannot be a relative extremum. If f prime of c is positive, that means the tangent has a positive slope, and the curve is approximated by the tangent, and the upshot is that if you take a value of x just to the right of c, then the tangent is slightly higher at x compared to c, which means f of x will also be slightly more than f of c. On the left, that reverse happens. If f prime of c is negative, this is switched, which means that at a relative extremum, it is a relative maximum or a relative minimum, either f prime of c should be 0 or f must not be differentiable. Either one of these can happen. A number c such that f is continuous but not differentiable, or f has a 0 derivative at c, is called a critical value. Well, the critical value is the name our textbook uses. I will try to use it, but it's somewhat unusual. If you look at other calculus books or online videos from other sources, you will often see critical values referred to as critical numbers, or often mathematicians call them critical points. Textbooks seem to reserve the name critical point to the point on the graph rather than the x-coordinate. But when we go to multivariable functions in chapter 17, they will use critical point both for the point in the domain and the point on the graph, and usually context will make it clear. In any case, I will always try to refer to these things as critical values. But I might sometimes slip up and refer to a critical point when, according to the textbook, I should be saying critical value. So let's look at an example of these and the illustration of this theorem. I have here the graph of a function which is defined in this interval from this number to this number. A is the highest point on the graph, which means this is the largest value of the function, so it's the global maximum. But there's another relative maximum. A is a relative maximum, but so is D, because if I take some small interval around the x-coordinate, or equivalently, if I draw a small circle around the point D on the graph, then that's the highest point on that small portion of the graph. So even though if you go far enough away, you can find larger values, if you don't move very much, it's the largest value. So basically, a relative maximum is a peak in the graph. It may not be the highest peak, but it's a peak. Relative minima are where the situation is reversed. These are bottoms of valleys in the graph. So here I have a small valley. B is the bottommost point, so it's a relative minimum. The lowest value of functions, lowest point is f. We'll come back to this in just a minute. But note that there are other critical values. A is a critical value because there is a corner. The function is not differentiable. B and D are critical values because I have a horizontal tangent, which means the slope or f prime is 0. Turns out at C also I have a horizontal tangent. So the graph is going up, levels off, but then starts going up again. If you're climbing a mountain, there might be places where you have a very short plateau. So you get level portions in the path, and those are also critical values because f prime can only tell you about the tangent at that point. It cannot tell you what the tangents are at nearby points. E is also a critical value because it's a corner, which means the function is not differentiable. So these are both critical values, but neither is a relative maximum or a relative minimum. So already noted A is the highest point. The lowest point on the graph is F. We are not going to call this kind of point a relative extrema because I don't have any part of the graph to the right. Now we can use one-sided derivatives to talk about these types of extrema. But since we haven't done anything with one-sided derivatives, and also because this is quite complicated, we are not going to really work with these in terms of the derivative. This kind of behavior can happen only at the endpoints of the interval. There are just two of them, so we can just look at them individually. So that's what we will do. So remember that if you have an absolute maximum or absolute minimum at one of the two endpoints of the interval, derivative cannot find them for you. You have to check them separately. This concludes our first list of basic definitions. There will be a few more later on, but this is what we will use to start. Goodbye for now.